Good evening to everybody. I'm representing Data Intelligence Group in Artificial Intelligence team in Samsung Electronics R&D Institute. And today I would like to say a little bit about how to port deep neural networks, or in general neural networks, for the embedded and mobile. I will tell about some selected topics and the problems which must be solved. I will start with the introduction and problems which we encounter, and then I will talk about two approaches which are the most popular. I wanted to scare you a little bit, and I put one slide with equations, and as Stephen Hawking said, if you put an equation in your book, then you probably will reduce the number of readers by half, but you're still here. So very short introduction to deep networks for those who don't know. So our networks are composed of layers. We have input, we have output. The input, for example, is an image. Output is a information what we found on the image, and this network is organized by layers. Each layer consists of neurons, and each neuron in the next layer is connected with some or all neurons from the layer which was before. And from the engineering point of view, each neuron is a kind of simple operation. You just take the inputs, multiply by weights, then sum up everything, give some bias to the result, and then there is an activation function which in fact usually passes only the positive values. Negative values are just put to zeros. So everything is about multiplying vectors by matrices and so on. So if we have a good library for this operation, we are here. This is just for the introduction. I will reference this later. Now let's go to our topic. One of the 10 trends of Gartner's is for this year is intelligent things. But the question is, where is the intelligence? Usually, all these devices, if they have to perform some intelligent task, have to connect to the cloud. And when they are not connected to the cloud, they become dumb. Oh, most of them. So our goal is to make this. And another thing is that intelligence, in most of cases, means neural networks now. So the deep learning is a buzzword, but deep learning is also something which all the solutions like machine translation, image recognition employs a lot. So we have to do it on the devices, mobile devices, on embedded devices. What problem can we face? There are mainly 4 problems. There may be more, but the 4 are the major. First is the power consumption and battery life. If we want to port these calculations on the especially mobile devices which are not connected, we very shortly run out of battery, and that's all. The other thing is that these devices have limited computation power when you compare to these devices when we learn the deep networks. The third is the latency. So we want our applications to work real time. So we don't want to wait for the response too long. Therefore, we have also to solve some problems with that. And the last but not least is the memory usage. I will show you where is the problem. First, start from the power consumption. Okay, we're doing the calculation on the mobile device, on embedded device. We can calculate that, for example, the arithmetic operation of floating point or fixed point consume a little bit of energy, like here. But the real problem is with the memory access. As far as we use the cache or static RAM, it's okay. But usually we have large models and they only can be fit into the dynamic RAM memory. And as you see, it's about 2 orders of magnitude more power consuming. So if, for example, we take a neural network which can compute, recognize objects, it has 1 billion parameters, and we read them from memory or write to memory, and we want it to work real time, 20 frames per second, then we lose 13 watts. So we have approximately several minutes to 1 hour, and then forget about the battery. Another problem is the computing power. Okay, I have here this the floating point operation. The neural networks are all about working on floating point numbers. So in practice, if we want to make a forward calculations for the typical neural network for the object recognition, like VGG or Microsoft Residual Network, which is very deep, we need approximately 10 to 20 gigaflop per second. So if we compare this to our performance in theory of devices like Galaxy S6 here or Raspberry Pi, this is in theory, you never reach this. So you can say that you are capable of, if you use this theoretical power, to have 2 or 1.5 frames per second. Yes, it's real time, yes. Next, we're talking about the latency. The latency is usually, if we do the calculation, we layer by layer. So we want to do some calculation in parallel, but there are points in each layer. We have to synchronize the data. So we will always wait for the slowest thread, which is calculating. And if we have very deep networks, we have many synchronizing points. The other thing is, again, with memory, if we use the cache, we are fast. But if you use dynamic RAM, it's 7 times slower. And the last but not least, I know that if you are aware that for the object recognition to work, we need, for the VGG, one of the popular deep neural networks, we need 850 megabytes of memory. And this is, I think this is only for the parameters, not counting buffers and intermediate results. The same is Microsoft or GoogleNet, they're also popular architectures. So if we compare this with our devices, this is the typical for the mobile. So we have dozens of gigabytes. Okay, for the model, yes, we can store the model there. Then we have RAM. Okay, we fit, but other applications have to be put away. But if you want to do it fast, we can use cache. Okay, we have up to 8 megabytes. So how to do it? There are many approaches. First is to try to compress these networks. By compressing the network, I mean we can remove, for example, some connections from our network. We can do it before training these networks or after training. If we do it before training, this is something which you probably know. We start from the fully connected layer, so the neurons are connected to all the neurons from the previous layer. Then we can think about, okay, if we are analyzing images, we can only make the local connections. So we can analyze subareas. We do not want to analyze image as a whole. We can analyze it in subareas and then aggregate the results. So we have removed some connections. We make the locally connected. Then this is what makes the object recognition possible. Somebody said, okay, we can look locally and additionally share the parameters. So no matter when we look, we use the same parameters of the neural networks, and this is why the result was the convolutional neural networks. and we can use it extensively. So before we are training the neural network, we just reduce some connections in an intelligent way, smart way, and share some parameters. Therefore, we can have the significant model size reduction, and in fact, this solution is easy to parallelize with good cache use. But the problem is that we cannot use it for all solutions. For image processing, it's okay. From audio processing, there are problems. For other tasks, it's not so simple. Additionally, it is hard to learn the networks, especially hard to fine-tune the networks for new tasks if we use only the convolutional neural networks. This is the problem we faced. Okay, so maybe we will try to do it other way. We train the network in the cloud using high-performance GPUs, and then try to reduce connections. Okay, we can remove connections. For example, if we notice that some connections, some weights are near zero, we can just give it a zero value. Then we can notice that some nodes in our network have no incoming or no outgoing connections, so we can remove them also. And last but not least, this is the runtime pruning. We can see that during calculations, some results, some outcomes from neurons are zeros, so we don't have to pass it. We can skip them. And okay, it's possible, but there are other problems which arises. We have to because most frameworks for deep learning is based on libraries which use dense matrix by dense vector multiplications. We have to use the sparse version of this. Okay, there are possibilities. For NVIDIA, we can use sparse. From Intel, we have also the similar library for sparse matrix, sparse vector multiplication. We have to change the structures from dense matrix representation to compressed sparse columns rows. But the problem is we do not have such speed up like with the dense multiplication, because we don't know how the weights are, which weights are zeros, which are not beforehand, and so we don't know how to divide the workload in the when we are doing some task in parallel. So we have several threads, and we have to say, okay, you calculate this, but we do in a dense matrix operations. We just say, okay, you take this two rows, the other thread takes another 2 rows, and the workload is even. But if we do a calculation with sparse matrices, it's not so obvious, it's not so easy, and there are many other problems. Okay, so maybe other solution. Quantization. Okay, we can remove the connection. Also, we can change the number of bits to represent the our parameters. So first try is to usually when we're doing scientific calculations, we use double precision. So it's 64-bit. But for the purpose of neural networks, 32 bits is enough. Single precision is enough. And as a matter of fact, most frameworks for deep learning use 32 bits. There is also representation half bits. Okay, but the problem is we really have a very low precision, only 10 bits for the precision. We have reduced range. Most architecture now support this. So we have the ARM CPUs, GPUs which support this. A new NVIDIA cards also supports the Pascal family and some of the Maxwell. But we have the significant precision and range loss. And as a matter of fact, we have only speed up twice because of memory. So maybe use fixed point calculations. So forget about using floats. We just take the integers and we fix the point somewhere here. The problem is we have the variable precision. So the larger numbers are better represented than the smaller ones. We have to keep in mind to normalize the values, the calculations, each time we have to scale. And it's rather not possible to train on the integers on the fixed point calculation, so we have to use the floats and then to quantize to put it to the integers, but it's not a problem. It's not a problem. The problem is how to use it on mobile devices. On mobile devices we don't train. On mobile devices we use these networks, and the core operations like multiply and accumulate MAC, it's 1.5 to 4 times faster on most architectures. And what is the most surprising, or maybe not, that there are many platforms which do not have floating point operations, the embedded platforms and mobile platforms, and they emulate this, and it's a disaster. So we have to use the integers there. There is another approach. We can just try to make non-uniform quantization. So we have an example here. We have the weights, this is the distribution of weights. After pruning, you see that around 0 there is nothing. And we see that if we represent it in a uniform way, so we have this quantization like these crosses. And we see that some of them will be not represented at all. So maybe we'll try to make some clustering algorithm to find some kind of centroids. And then, of course, we must use the code books or lookup tables before the calculations. It is working. And as a matter of fact, I will show a reference to the article, to the paper, in which they are claiming they can use only 4 to 8 bits, and it's enough for, and the neural network does not lose a lot of its accuracy. Here's an example. This is a pipeline from one of article. The reference will be at the end of the presentation, in which they take the classical neural networks, LeNet, AlexNet, and VGG, and they do it in the way you see on this pipeline. So first they make a pruning, but they train the networks, then prune the connections, and they retrain and prune and retrain and prune to the moment they found that there's nothing more to be done, and they see that they have 9 to 13 reduction in the size. Then they use the quantization. So they cluster the weights, generate the code book, and then again train, retrain code book, train, retrain book. And at the end, they do something only for storage. So they use the Huffman coding to compress these neural networks, but only for the storage. So they have 35 to 90 to 49 reduction in the size. And if you see the parameters here and the compress rate, you will see that, for example, the AlexNet, which originally have 240 megabytes, have 6.9 megabytes. So it will fit in the cache memory. And you can imagine what does it mean. Okay, the compression is the one thing, but we can also decompose the neural network. So if we find that our network is too large, we can just cut some layers from the top and put layers with less neurons or less number of layers and retrain. You can even do it in some architectures without retraining. This is an example. This is the GoogleNet, one of the neural networks for the classification from images, and it has some back paths, which in fact also classifies. This was used to solve some problem with vanishing errors during the training. But you can just cut this part of the network and take only this part without the training. The results here for some applications are enough. The reduce is significant. And at the end, I would like to give some equations. This is, I think, one of most interesting things. we can alter the neural network inside. So we can take some layers. As I said, here you have the example for the fully connected layers, but the same is for the convolutional networks. A little bit complicated, but so usually we have the operation like we multiply our input from the previous layer, output from the previous layer by the matrix of weights, and they add up by us, and we have the activation function. Now we can try to, this is the matrix, so we can decompose the matrix. We can decompose the matrix into product of two matrices, which approximate this matrix, but which have low rank. So, for example, we have two rectangular matrices, and when you multiply them, we have approximation of this. So, in fact, we just introduce some bottleneck, some layer inside, which has, let's say, L neurons in this layer, and we can manipulate this L value. So we trade off between the accuracy and size. Before this decomposition, we have n multiplied by m weights in this matrix. After, we have this one. So if we choose the L parameters wisely, we can reduce the size of the network and keep the accuracy. And this can be done by, if our matrix is rectangular, we can use the principal component analysis for that. Or in general, we use the singular value decomposition, and we remove the singular values, which absolute value is the smallest. And I think this is all I would like to say today. At the end, there are the references to articles, which are, I think, the most interesting in the topics. And of course, if you want to work on such interesting things, I encourage you to join us. Thank you very much.
Thank you. So, time for questions. Are you ready?
Hi. I have a question regarding the composition on the last slide you showed. You were doing matrix factorization after learning or before learning?
Usually, you first learn the neural networks, so it's large. Then you do the decomposition, and then you can retrain it again. So usually additional retraining gives a little bit more to the accuracy, but you can use it without the retraining also.
Okay, and I have the second one regarding the pruning, the architecture of the neural network. We can say that if the weight is really small, for example 0, then it's not relevant. It says that the feature is not relevant. But we also know that if we remove the node, that another weight may blow up. So I think one of the reasons for the dropout in the regularization technique is that I forget the word, to distribute the competency of the neuron. Okay.
Yes, this is the problem. You're talking about the problem of overfitting. So the neural network.
If you remove the weight, you may cause the other weights to blow up, or this is my concern.
Yes, if you try to then retrain this and again prune and retrain, yes, you have to be careful about that. But if you only do the pruning, then you remove just this small weights. So usually this neural network works okay, and the accuracy is just a little bit smaller than before the pruning. And it depends, of course, of how many connections are removed.
Okay, thanks.
No more questions?
So what is the final speed up of your optimizations? Can you manage to run those computations online real time for each frame, or still you have to, this is just a step, or this is the final solution and it's enough?
The answer is, there are two answers to this. First is, it depends. The second answer is you will see in the Samsung products.
When?
One Samsung product was unpacked today.
Okay. So TechCrunch or something.
Thank you very much.
Okay, one more question. There's one back.
Okay, I got a question again about this PCA method. So why do you need PCA at all? So could you just introduce bottlenecks and just train the network? Or the PCA just is the purpose of PCI is just to identify the bottlenecks?
Sometimes you have a good neural network trained for cloud use or for the GPU, and you want only to change the domains, transfer, to use it in the other way. For example, you have the neural network for recognizing millions of objects. You want to recognize only 1,000 of objects. So you don't want to waste your time to retrain everything. You want to use as much as possible from your network, from the features that the neural network learned so far. And this is why you introduce this. Of course, there is another way. You can just introduce the bottlenecks before, but then you face some problems with learning. So sometimes it's better to have this bottleneck introduced before training. Sometimes it's better if you have the models. You just take train models and just decompose it to use it. For example, you have a neural network for some task like object recognition or machine translation, language translation, and they are for the server deployment for the cloud. And you want to use the same, but on the mobile. And you have your timeline, and you want to make it fast. So this is why you use this method.
Okay, thank you so much.
Thank you.